good afternoon, everyone here. So my name is Ling Feng from School of Computer Engineering from NTU. So this afternoon, these sessions will have three speakers, right? We have three great men talking about the microscopic world, okay, microscopic technologies. Our first speaker will be Professor Stefan Hell. He is a director of the Max Planck Institute of Biophysical Chemistry in Göttingen. He's also leading the optical nanoscope division in this German cancer research centers in Heidelberg. Okay. So Professor Hell is a pioneer in the field of nanoscopy, for which he has received a few awards, including the recent prestigious Kerber European Science Prize in last July, I think, right? Yeah. I hope it's not too late for us to congratulate Professor Hell for his great achievement. So this afternoon, he will be talking on the topic on this nanoscope with a focused light. Let's welcome Professor Hell.
Thank you very much for introducing me and for having me here at this wonderful meeting. The audience, I think we're all familiar with the expression, a picture is worth 1,000 words, or seeing is believing. And therefore, I don't think it's a coincidence that the beginning of the natural sciences as we know them today very much coincides in time with the invention of the microscope, or of the light microscope to be precise. Because with the light microscope, we could see for the first time that any living being consists of cells as their basic units of structure and function, and with the light microscope we discovered, for example, bacteria and so on. However, we also learned at high school and definitely at college that the resolution of a light microscope, the ability of a microscope to see the small things and determine small things separately in space, is fundamentally limited by the wavelengths of light. So if you want to see finer details than about half the wavelengths, which amounts to about 200 nanometers, that is not possible. Now, for that reason, the electron microscope was invented in the mid of the 20th century, and the electron microscope, by resorting to focused electron beams rather than light, has achieved a much higher spatial resolution. And as a result, we have discovered a new world. We've seen, for example, viruses for the first time, or subcellular organelles, such as the ribosome, and in a number of cases, it's even possible to have a spatial resolution that goes down to the size of a molecule or to the atomic scale. Now, I'm going to talk about the resolution of a light microscope, and hence the question, why bother now that we have the electron microscope? Now, the answer to that question is relatively easy. If you want to look inside a cell in 3 dimensions, non-invasively, especially inside a live cell, non-invasively, or even living tissue, there is no alternative to using a light microscope, a focusing light microscope, because focused light is the only way, or the only means by which you can penetrate into a cell non-invasively and get information about what is going on, for example, at a protein level. So for that reason, it made a lot of sense to readdress the resolution issue and to ask, is there really no way, is there really no physics or physical chemistry out there in this world that would allow us, in the end, to get pictures that have a spatial resolution that is far beyond the diffraction barrier, truly in the nanometer range, sort of electron microscopy. Now, today we know that this is possible, at least for the very, very important imaging modality, fluorescence imaging. And I would like to guide you or to explain to you the basic principles that have allowed us to overcome the diffraction barrier. And of course, I would like to give you a flavor where the field is developing to. What can you do today with it? Now, why have people thought that the resolution of a focusing light microscope has come to an end? It's very simple. The most important part of a microscope is the objective lens. And the role of this objective lens is to focus the light down to a point. But as we learn at school, because light propagates as a wave, the lens will not be able to concentrate the light on a single point. Rather, the light will be smeared out in the focal region, forming a blob of light that is at least about 200 nanometers in the focal plane and about 500 nanometers along the optic axis. And this has profound consequences, because if you're having several features falling within that range, they will be inevitably illuminated at the same time, they scatter off light at the same time, they fluoresce at the same time, and so the signal that is generated here more or less simultaneously will be confounded by the lens. So if the lens collects the light again and directs it to a detector or so, we'll not be able to tell it apart. Now, the person who realized this problem first was this man who can barely see here, Ernst Abbe. And he coined this diffraction barrier in an equation which is still named after him. It's saying that in order to be separated, two features of the same kind have to be further away than the wavelengths divided by the so-called twice the numerical aperture of the objective lens. This is this number. That amounts typically to about 2 or 3. Now, you can find this equation basically in any textbook of physics or cell and molecular biology as well, because of the enormous relevance of the light microscope to these fields. Now, Ernst Abbe has had many contributions to optics, but for some reason or good reasons, this diffraction barrier is regarded as his most important legacy. Because if you happen to travel to Jena, where he lived and worked, that's a university town in Germany, you will find this memorial erected in his honor and this equation written in stone. And this is what we want to beat now. We would like to show that we're able to distinguish features of the same kind that are closer than this distance of d. Now, if you want to do that, of course, we cannot wait that this problem is sorted out by technological progress, because this is not a technological problem. So the lens won't get any better. The lens was already good 130 years back. And of course, the resolution problem will not be solved by having more sensitive detectors like better CCD cameras. Of course, detection sensitivity has evolved over the years. In fact, it's possible to detect even single molecules. However, if two molecules come very close, closer than the distance of d, we will not be able to tell them apart. Resolution is about the ability to separate small things, not about sensitivity. You can be as sensitive as you want, but if they come very close, closer than the distance of d, you reach a limit. And this is the problem that we want to fix. Now, if you want to fix this problem, you can only fix it by taking a different view on the problem, having a different angle on this, say, century-old problem. Now, the view that I took on is, well, the lens will not be able to do a better job, but maybe the molecules that we look at, they can perhaps help us to do the job. Maybe there's features in the molecule out there that would allow us to separate them in the end and get sharper pictures. Why is that? Because molecules, as we've heard today, they have energy states, for example, a ground state and an excited state, and these energy states and the transitions between these states may eventually help us to tell them apart and to get much sharper pictures. Now, you excite them, you get fluorescence, and as you see, these processes going up and down will help us to overcome the diffraction barrier. But of course, it's not enough to have a rough notion. You have to come up with something that really works and turns out to be workable in practice, applicable, and then useful in the end. Now, a concept that turned out to work was this concept called stat microscopy. And you can briefly see what it looks like. You have here an objective lens, and the role of this lens, of course, is to focus the light down to the focal region. So what will happen? We will excite, of course, molecules here with excitation light that is focused now by the objective lens. And the lens, of course, will not be able to concentrate the light further down than to about these dimensions here. You see? 200 nanometers at least. So all the molecules falling within that range will be illuminated at the same time. They will give off light at the same time, collected here by the objective lens, and go this way. And so we will not be able to separate the strands that are produced, that are in the focal region in here. Now, what could we do in order to separate them? We could say, okay, if we manage to reduce the signal here to the signal that is produced by the molecules here in the center, then of course we should be able to get a higher spatial resolution. Because we could maybe separate them because they're not giving the signal at the same time here in the detector because it's not integrated here. Then you have to ask yourself, is there any mechanism out there that would allow us to stop some of the molecule to emit, despite the fact that all of them are flooded at the same time by the excitation light? Now, if you're trained as a physicist, then you know not only you can excite a dye, but also you can de-excite a dye. So you can put in a beam of light, the role of which is just to silence the dyes, to keep them silent, despite the fact that they're flooded with excitation light. And that beam is inducing a phenomenon called stimulated emission. It basically means that it kicks down the molecules from the excited state to the ground state while they are staying here in the excited state for typically about a nanosecond. In order to do that, the beam has to be redshifted in wavelength so that the photon energy is not sufficient to excite them, but it will de-excite them. It will kick them down. And so they will not be able to emit. And now you can imagine what we want to do. We modify the beam, this beam, such that it silences, of course, molecules that are located, say, sort of the outer rim in here. And now you see that, well, although here these molecules here are flooded, some of the molecules at the outer rim, of course, are stopped, and so we must get a slightly higher spatial resolution. But of course, we are not there yet. We just want to confine, of course, the fluorescence to the signal that is produced in here. And so what do we have to do? You could say, make smaller rings. If you have smaller rings, then it should be possible to see more specifically the strand here in the center. But Abu would say, no way, you can't make smaller rings because that's also limited by diffraction. Now, fortunately, we don't have to do that. Why? Because in order to shut them off, the only thing that we have to do is we have to make sure that the beam here is bright enough such that the molecules are getting dark. And this happens if the beam crosses a certain intensity threshold, and this is shown in here. If it's past a certain threshold, you can be sure that the dye is silenced, that it's turned off. And so what we do now is to make it strong enough such that even in these regions here, so that are closer towards the diffraction barrier, here closer towards the center, the molecules are silenced. And now this is what we want, because now we just see the signal here from this strand, but not from the other strand, because we've silenced the molecules. All of them are flooded with excitation light. No way out. We can't change that, no way. But only these in the center here are allowed to emit. And this helps us to get beyond the diffraction barrier. Now, how do we get the rest of the images? Well, it's very simple. We have to see them and shut them off sequentially, as it is shown in here. If we go from one to the next, like this, and now we can separate these two from those three, and so on, and we move on, we proceed like that, and in the end, of course, we can separate the strands, and now we should get a much, much higher spatial resolution, at least on the paper, of course. So that's the concept. In order to realize this, of course, several steps had to be taken. First, you have to publish it, convince an editor that it works. Sometimes not that easy, especially if you claim that you can go fundamentally beyond the diffraction barrier. Then you have to convince somebody to give you a job once you have a paper, and then, of course, you have to convince somebody to give you the money, which is also not easy, to make this thing workable. In the end, you have it, then you have to sort out the physical and chemical challenges in order finally to convince the world that there is a world beyond the diffraction barrier. And so it worked out. I would like to show you comparison images just to show you that, well, we can have a spatial resolution with focused visible light that is much better than has been, in the best case, achieved until then. Now, this is on the left. The standard is called confocal microscopy. So it's a very high-end spatial resolution, but now you have it on the right-hand side. You can clearly resolve these beads here just by using, see, the molecular transitions here in the dye. And this is telling us that we can fundamentally overcome the diffraction barrier. Now, I have the impression that the contrast here in the monitor is not at its best, so I'm trying to make a little experiment ad hoc by just restarting this, if I'm allowed to. Because it looked much better during the break. So I don't know if it helped, probably not. Anyway, I think you will get the gist of it. These are individualized molecules. You can clearly see them. Here they are separated, here they're not. Why? Here they were illuminated at the same time, gave off light at the same time, but here no. At the time this one was emitting, this one was stopped. At the time this one was emitting, this one was stopped. And so we can, just by playing with the molecular transitions, separate the features. Now this is an example of protein on a plasma membrane of a cell. You see, initially no way to separate them, but the stat microscope, as we call it, tells us these are little clusters that we can clearly discern. Now, initially, we worked with relatively complex laser systems to be very flexible, good reasons. If you don't know how it works, or if it works, and to which extent, and where the limitations are, of course, you have to be flexible. And of course, this gives nicer images. Meanwhile, we understand it much, much better, and so you can resort to relatively compact laser systems. And this is something we set up for a lab course, and this is the type of picture the student gets. So it has become routine. It has become a routine to the extent that it's commercially available. There is a third generation now on the market, and of course there are new generations coming up basically every 2 years. You can use it like a standard confocal microscope. Put your sample, push button, take your images, but of course the spectroscopy has to be adjusted to the dye. You have to have the right wavelengths for excitation, and you have to have the right wavelengths for stopping the fluorescence. And therefore, applications in various fields have been made. I would like to touch just base on a number of applications, more recent applications, to give you a feel for what can be done with breaking the diffraction barrier and having sharper pictures. Well, this is an application we did quite early on with a collaborator who came to my lab. He invented this protein. He found this protein with this funny name, Prof. And so he felt that there must be a substructure in here. Stat told him, yes, there is a substructure. You can see it now very clearly. It forms this little basket. So we continued on this collaboration recently by labeling all kinds of proteins here in this protein complex, in this neuromuscular junction of fruit fly larvae to sort out the proteins in the presynaptic active zone. And these are, say, 2 color recordings. Now you see quite nicely that it forms these little baskets, and so you can come up with a model how the proteins are arranged. Here you see almost nothing. It's very, very hard to distinguish it because you don't have the spatial resolution. And of course, you can do this now with all kinds of proteins. You put them, different labels on them, and you can, in the end, sort out the distribution of these proteins at a nanometer scale. And this is kind of interesting because look at the numbers here, 50, 30, 70, 80, 100 nanometers. This is far below the wavelengths of light, which in this case was 700 and 750 nanometers. Still, we can sort it out because we have a spatial resolution beyond the diffraction barrier, despite the fact that we use focused visible light. What helped us to get there? The transition of the molecules. The molecules helped us see them, so to speak, see features sequentially by shutting some of them off. Now, this is an application in a living heart cell, myocardial infarction. So this is a control. This is 4 weeks after myocardial infarction, and this is 8 weeks after myocardial infarction. So why did we do that? We wanted to see how this T-tubular network, that's what it's called, changes over time. And so you can quantify it because you have the high spatial resolution. If you don't, no way to quantify it. And so you can see how this T-tubular network changes progressively over time, and you can quantify it. Another example, HIV infection. Now, it is known that HIV has a protein which is called ENV, and this protein sits, so to speak, here at the outer rim, so to speak, at the shell of the HIV particle. Now, it wasn't known, however, it is distributed. And so this is the confocal recording, and this is the stat recording. Now you see, the confocal, well, it's all blurred, but stat tells you, oh, it forms patterns. And in fact, as it turned out, by doing, of course, parallel biochemical experiments, that this distribution of this ENV protein correlates with the maturity of the HIV particle. So to cut a long story short, in order for the HIV particle to infect the host cell, it has to grab all these ENV proteins in a single place to be effective in entering. So this is a kind of insight is gained on the mechanism of infection of HIV. Now, you've seen now living cell, viral particle, and so on. What about animal? Can we look, for example, into a living animal? Well, as far as optics allows us to do so, yes. So we made an experiment, well, to help neurophysiology. So this is now a mouse, a living mouse, an anesthetized living mouse. And we open the skull of the mouse and focus the objective lens right onto the molecular layer of the somatosensory cortex of the brain of the mouse. And what you see here is a picture of a neuron from the brain of the living mouse. So this is a transgenic mouse, which was labeled here with a yellow fluorescent protein to indicate the neuron. And now you see, with subdiffraction spatial resolution, here the dendritic part of the dendrite and the so-called dendritic spine. So this has little protrusions that are very important because these are the receiving ends for the information to this neuron when it comes from the outer part. And because of the high spatial resolution, what we see here is what it looks like, and not only that, we could detect, and if we zoom in now, that it makes little movements. So we can take movies because this is focused light. You can take movies. So this is a strength of such a method. So it has known that, of course, and it's anticipated for a small animal or so that has developing brain, there must be morphological movements. But here it is shown for the first time that even in the adult mouse, you can have these little movements. Obviously, when we learn something or information is processed, not only the synapses are strengthened chemically, but also the neuron has to adjust a bit itself to be able to receive the information properly. So that's the outcome here. So this is a spatial resolution of about 70 nanometers, in this case about 3-4 times better than the best, say, confocal or so-called multiphoton microscope. But there's also, of course, applications outside the life sciences, material sciences. I like to show this because it's fun to show. So this colloidal crystal formation, now you watch these colloidal particles at very high speed. So the recording speed is 200 frames per second, so 7 times faster than display. Now you see it in a second with a normal resolution. No way. You can't see anything. Here you see what it looks like, and you can learn something about how this colloidal crystal forms. Now, what is the speed limitation? The speed limitation is just given by the brightness of the molecules. Again, the molecule is the facilitator, but also the limiting factor. So the better molecules we have, the better the images we'll get. So what is the obtainable resolution? Talking about limits. Have we pushed now the resolution of the microscope to a new limit or so? Say, what is the limit? Is it now 30 nanometer, 20 or 50, or what is it? I think it's worthwhile spending a few thoughts on this problem. Now, as you can guess, the resolution will now depend just on this dimension D, in which we produce the difference in states, like the on state and the off state. Now, this value of D, of course, will decrease if we crank up the power of this off-switching beam, of this, say, turn-off beam, of the red beam that doesn't allow the molecules to emit. And clearly, the higher the intensity will be, the higher the resolution will be. So the intensity will determine the D, and D cannot be given by Abbe's equation anymore, no way. And so it has to be in the denominator. But clearly, it's not just the absolute value of the intensity, it must be the ratio I over IS. If you have a large ratio I over IS, then D must become very small. Now, if you do the experiment or the calculation, then you will see it scales inversely with the square root of I over IS. Now, this equation is sort of okay, but it has a little caveat, as you can see. If the intensity gets 0, if I get 0, meaning that if we turn off the red beam and we have a normal microscope, of course, then, of course, in this equation, D would go to infinity because we divide by infinity, but that's not what we want. So we fix that, we put in a unity. And now this equation is fine, and it describes the situation actually quite well. It means we can tune the spatial resolution. We can adapt the resolution to the problem. So if you grab more signal, more molecules, then you can be faster because you don't have to make such a denser pixelation because you switch off fewer molecules on average. That's the point. Or, of course, you can have a higher spatial resolution. But from a conceptual viewpoint, there are two things. This concept showed you can overcome the diffraction barrier by playing an on-off game, as I like to call it. And secondly, of course, in concept, if you have two molecules coming very close, like here, you can't separate them, obviously not, because they are illuminated at the same time, give off light at the same time, and there's no way for the detector to tell them apart. But what do? We make sure that we switch off also the other one, so there's only one, in this case, just that one that fits in that tiny region which fluorescence allowed is emitting, and then we go to the next. Just a few photons are enough, and then we can separate them. And so we can, of course, conceptually have resolution at the molecular scale, despite the fact that we use focused visible light and ordinary objective lenses that have reached their technical limits already 130 years back. So the diffraction resolution barrier is not shifted to a new barrier, but is conceptually overcome. And it means if we sort out the technicalities, especially the molecules, that's important, we can have molecular scale resolution with visible light and regular lenses. And that is reflected in the equation, because if I becomes large over IS, what will happen? I mean, you can tell. High school mathematics, it goes down to 0. And this can be taken almost literally at least the size of a molecule. So you have two molecules coming very close, you can separate them. Now, what does this mean in this concept? I becomes large over IS, or IS is small with respect to I. Well, it means that this curve becomes very steep. So you have an almost perfect on-off switch, so steep on-off switch. Of course, if you have such a steep on-off switch, then you should be able to make these differences in states very, very sharp in space, and hence you get a very high spatial resolution. Now, with organic molecules, that's not so easy to accomplish unless you make the molecules better, but there are inorganic, molecular-like systems that behave like molecules and with which you can demonstrate this. And so we've done that. And these are so-called color defects in diamonds, so-called nitrogen vacancy, to be very precise, charge nitrogen vacancies in diamonds. And they have the feature that you can shine light of them, and they do not photobleach. So you can play this on-off thing as often as you like, and the power that you can put in as you like. And this is now not a cartoon, this is a true measurement. So here we demonstrate this very steep on-off switch, and as a result, as you see here, we squeeze down the area in which the molecule, or molecular system in this case, is allowed to emit to very small dimensions, 8 nanometers, coming from about 220 nanometers. And just by using the transitions between the states, the bright state and the dark state, kicking it down from the bright state to the ground state, making sure that when it's off this little area, it's not capable of emitting. And so you can take sharper pictures. For example, here, this is a standard resolution of defects in diamonds. And here, you can separate them. You can see them very, very clearly. Now, they are separated, and you can infer from the brightness, they have about the same brightness if you look at those, of course. And so you know these are individual emitters, because the resolution is good enough so that the density here in the bulk of the diamond is such that these are individual emitters. Now, once you know, or you can safely assume these are individual emitters, of course, you can find out the position of these individual emitters with much higher precision than just the separation capability, the spatial resolution. How do you do that? Well, you just calculate the center of gravity of each of them. And if this is very bright, if it's a very strong signal, then you can very precisely calculate the center of gravity at which position the emitter must sit. And so this has been done here, and because this is so bright, this went down to about 1 to 2 angstroms. And you know now from high school, 1 to 2 angstroms, this is about the size of an atom. Now, at the risk of sounding perhaps dramatic or too dramatic, here you see nothing, nothing. No way to find out anything. Here, you see each individual defect, this molecular-like system, with the precision of the size of an atom, with a regular objective lens and focused visible light. In fact, the wavelength here was 770 nanometers, so near infrared. It tells you something has happened. But while you may be impressed by this, a word of caution. Not this is the decisive step. Certainly not. This is just calculating where it is once you've separated. Separating the feature is the decisive step. This is the decisive step. Once you've separated, then you can make this calculation of the position. So why can we separate them? And in the previous case, we couldn't. Why? Because at the time, this one was emitting, this one was turned off. And at the time, this one was emitting, the rest was turned off. So playing the on-off game, separating is done by making sure that the neighbor is not capable of emitting when the feature of interest is capable of emitting. This is how you separate them. So this on-off principle lies at the heart of this breaking of the diffraction barrier. And once you realize that, you know, oh, this must be actually a quite fundamental concept, and it shouldn't be just limited to this mechanism that I was talking about, the stimulated emission. Stimulated emission, to be very precise, is the most fundamental and the most universal way of turning a molecule off, because it directly acts on the fluorescence state. There's nothing more universal or fundamental than that. You just kick the molecule down, it's not capable of emitting, that's it. And this is why the concept applies basically to any fluorophore. But universality doesn't mean that it's the best for all cases, or doesn't have drawbacks. It has a drawback. Namely, you have to act within a nanosecond, because the lifetime of this fluorescent state, the molecule stays in the on state just for a nanosecond. If you have to shut it down to prevent this, then you have to act within a nanosecond. You have to put in relatively large intensities. You see here megawatt per square centimeters. And once you realize that, you say, oh, since this is about on-off and not just about this phenomenon of stimulated emission, maybe there's other on-off transitions in a dye that allow you to do the same thing, but perhaps at lower light levels, not that general as this, not that universally applicable, with more, say, restraints in the operation, but still with the advantage of using much lower power. Well, another option is to flip a spin and go to a metastable dark state. In that case, the molecule stays for longer in the off state, for example, a microsecond, and so on. You can use this mechanism to switch a dye off, and then you flood it with light, and only those that are on are capable of emitting. And of course, once you know that you can flip a spin, you can know that you can also flip atoms. For example, doing a cis-trans isomerization, so if in the cis state the molecule is emissive and in the trans it's not, just to make it up like that, you can do the same game as with the stimulated emission, but with the added advantage that the lifetime of the involved states can be much longer, milliseconds or even seconds. And that means you have more time. You don't have to rush putting in the photon so quickly to make this difference in states. And this difference in states, on and off, stays there for longer. So you have more time. And since you have more time, it stays for longer, you can reduce the power level requirement. Now, a way of playing on-off, of course, or implementing cis-trans isomerization in a sensible way in the life sciences is to use a so-called reversible, switchable fluorescent protein. And this is clear now as I said, the same game, but I couldn't have called this STAT anymore because, as you can see here, there is no stimulated emission. STAT stands for stimulated emission depletion. So, but still, so I had to come up with a different acronym, so I called resolve. The idea is the same. Switch off molecules, it goes here to the off state, so to speak, and then you flood everything with excitation light. You flood all the molecules, no way out. You won't do any better. But only these inner centers are allowed to emit. The rest will be shut off. And so we see only those, and how do we get the rest? Well, you know it by now. We just scan the beams across the specimen and sort out everything that lies within that 200 nanometer range. Now, I would like to show you that this concept, resolve concept, works. We have worked hard on it during the last year because initially the molecules that we found, or that we had, the reversible switchable proteins, didn't do enough on-off switching cycles. But now it's possible to switch them on and off many times. And so this is just an example where you see a living neuron in a hippocampal organotypical slide. But this is now, it looks like STAT if you look at it from the resolution and so on. But it's no stimulated emission. It's this reversible switching between on-state and off-state by a cis-trans isomerization. Now, this is a protein similar to the famous protein developed by Atsushi Miyawaki, who has an important contribution to the switching of these fluorescent proteins. The point here is 1,000,000 times lower intensity than STAT. And so you can imagine, especially if you think about the mouse experiment. So we did that even with the high power, and the mouse was okay, and we could see details. But now we know there is no physical or chemical reason, so to speak, that will prevent us to do the same thing at much lower light levels. That means we can apply much lower light levels, penetrate deeper. I think there's no fundamental reason why we would eventually not be able to see details in the brain minimally invasively, so to speak, at very low light levels and at the molecular scale. And this is a very fascinating prospect. Because we can access now features, we can access molecular distribution that, yeah, we couldn't just dream of maybe 10 or 20 years back, or just thought it would never be possible. Now, this concept is not the only concept by which you can play the on-off game. Another very important concept was introduced, so Eric did that first, called PALM. And how does this differ here from this concept? It's very simple. Here we determine with a beam of light where the molecules are on and off. Here we don't. We don't have a structured beam of light like a donut or whatever. The molecules are switched stochastically from the off state to the on state in space, somewhere, at some location within this 200 nanometer zone. But yet you don't know where it is. So is this useful? The answer is yes. Because with the fluorophores emitting, say, many photons from the same place, once you switch in the on state, you can project it onto a camera. And then you can locate each position, and you can find out where it happens. And so you do it, switch it on, switch it off, go to the next, and then you assemble, so to speak, mathematically the whole image. Again, all the molecules flooded with excitation light, but only this one is allowed to emit, like here. All flooded with excitation light, but only here is allowed to emit. So this on-off makes a separation. But the way the on-off requirement is here is different to here, because here you need only one switching cycle to make an image. So this is a major strength of the stochastic concept, whereas in here you need many switching cycles. On the other hand, conversely, here you need many photons to find out where it is. Here one photon is enough. So each one clearly has strengths and weaknesses and different, so to speak, say, areas of applications. With the stochastic method, you can get very sharp images, come out very crisp. With the, say, deterministic method, like the STAT method, you can quickly take moving objects, images, because you have already the information where the photons come from. So this is just an example. This is the movement of synaptic vesicles in a living neuron, recorded with STAT. You can see how these vesicles move about, and of course with the normal spatial resolution confocal, you had no idea. You couldn't find them out. Here it's done at video rate. So it shows that we have several options to get to diffraction barrier, several options to implement this on-off separation capability. Indeed, this separation capability is a facilitating element. And this is the reason why we can take now the pictures, why we couldn't do that maybe 20 years back. Of course, it's always important to know where you are. So by defining with a beam of light that it's the molecules that come from here, that are here, that give the signal. Just as it's important to find out where it is. You have to do that, no doubt. But that's just a coordinate. The challenge is to separate them, to tell them apart. This has been the problem. And this is by using an on-off transition. So make sure that not all the molecules that are within this critical range of 200 nanometers are capable of emitting. Just only a fraction of them here, or only one of them. And this allows us to tell them apart. So it means that there must be some sort of inhibition, like an inhibition that prevents the molecule from emitting in both cases, despite the fact that it's flooded with excitation light. Now, what is the mechanism for inhibition? Well, you have to put it in a state in which it's not capable of emitting. So to be more general than on-off, it means we have two states, two distinguishable states, a state A and a state B. Once you have separated your molecules and have them transient in two different states, you can take things apart. And then once you realize that, you say, oh, does this need to be fluorescence? Do we have to have say, a fluorescent object in order to break the diffraction barrier? The answer is no. Of course, fluorescence, non-fluorescent is a very convenient way of doing it. But you can also be absorbing, non-absorbing, or scattering, non-scattering, spin up, spin down, cis trans. In fact, think about it. You can come up with your own set of states. Go home, think about it. Maybe you have a genius idea where you can break the diffraction barrier in the imaging, optical imaging, I don't know what, by having that in two different states. So why was it fluorescence, in my view? Why was it fluorescent that this worked out first? Very simple. Not only because fluorescence is very sensitive, and you get a very good, say, background suppression in fluorescence. It's very easy to disturb. You can easily disturb a fluorescent molecule, a molecule in its fluorescent state, because you can put light on it, you can relocate the atom, you can flip a spin. It's very easy to play on-off. This is why we broke the diffraction barrier first with the fluorescence concept. But it's not limited to fluorescence. It's very important to understand. Now, is it limited to imaging per se? No. Think about it. A could be a reactive state, and B could be a non-reactive state, for example. What does that mean? Well, it means, for example, that A could elicit a reaction, and then you could, say, make a polymerization, for example, beyond the diffraction barrier. I'm just showing a sketch. And you can write, of course, with the resolution beyond the diffraction barrier. I think this field is underestimated, because what it means, you can, in principle, focus with the light into a transparent sample and produce, in concept, any nanoscale feature. Just by focusing. No way to do that by X-rays, because you can't focus them. Electron beams get stuck. So I think this is a very, very important area which will allow us in the future to make materials that are not possible. So with that, I'm summarizing. So we've seen that Abyss diffraction barrier is broken, and imaging, and in theory, even writing, in some cases it has been shown already, beyond the diffraction barrier has become a fact. It has implications in many fields. For example, seeing distribution of proteins, or say material sciences, even measuring magnetic fields or neurophysiology to see, for example, the dendrites with a very, very high spatial resolution and watch the morphological changes in time. And to some extent, it's even applicable, say, to the brain of a living animal. Now with that, I'm acknowledging, of course, the people who had a lot of fun contributing to this development, to this journey. And with that, I'm coming to my final slide. Clearly, Abyss equation cannot account for everything that we've seen. I mean, it's very clear. So we have a higher spatial resolution, and we can go beyond this distance of d that is just 200 nanometers. Can we deal with that? Yeah, oh, yes. We just plug in that square root factor, and now we have this equation that describes the situation actually quite well. It's worthwhile spending two thoughts on this equation. Well, the first thought is the following. It scales with the wavelengths. It still scales with the wavelengths, and it must scale with the wavelengths, because we use focused beam. And therefore, it must scale with the wavelengths. There's no way out. But it doesn't matter, because it's not limited by the wavelengths. Why it's not limited? Because we put in this expression. And as you've seen, if we make this expression very large, then the d becomes very small. And so we can get past the limit set by the wavelengths without beating the wavelengths per se. It's still there, diffraction is still there, but it doesn't matter, because we can separate features. Why can we separate them? Because we have the molecules transiently in two different states. So what does this actually stand for? It stands for putting the molecules in two different states. And that's the secret behind the whole development. I think in the past, people were just focused on the waves, and they tried to overcome the diffraction barrier by, I'm saying it now loosely, messing around with the waves, trying to confine them with a small tip or changing the materials through which the waves are propagating. This is very, very hard. It works for a number of cases, no doubt, and it has some applications perhaps in the material sciences. But here, the notion is different. Forget about the waves. Let the waves diffract. They go out and they're going to diffract. But we separate by having the molecules transiently in two different states. That's the whole trick. So in simple terms, give me two states. With two states, you can take the diffraction barrier completely apart. That applies to imaging, that applies to writing. And the molecule is central, because it's about states. Thank you very much.